thanks for joining us as we give our update from Planetary, where our team is on a mission to fight climate change by enhancing the ocean's ability to remove carbon dioxide from the atmosphere. My name is Jen, and today I'm excited to share insights with you from our 2023 trial work in Halifax and what we've learned. Now I'm going to hand it over to Steve and Will for introductions.
Hi, thanks. Steve Rackley is my name. I consider myself a recycled or perhaps repurposed petroleum engineer. I spent 35 years of my career developing oil and gas fields around the world, and then kind of re-educated myself on carbon capture and storage and carbon dioxide removal technologies over the last 15 years or so. I've been working with Planetary for about 3.5 years, initially conducting a feasibility study for a pilot project in the UK, and then more recently focusing on the measurement, reporting, and verification challenges and our first steps on ocean modeling.
Thank you. Will?
Yeah, thanks. My name is Will Burt. I am the Chief Ocean Scientist at Planetary. I am located in Halifax, where we're going to talk about all our great work today. This is Halifax in the background behind me. I'm an oceanographer. I joined Planetary 2.5 years ago to lead their science team, and just been working with monitoring, modeling, working with Steve on all things MRV and getting these field trials up and running.
Awesome. Thanks for joining, both of you. Before we dig into the actual results, Will, would you mind getting our audience up to speed briefly on the work that did happen in Halifax?
Yes. So the Halifax trial last year was the culmination of about 3 years of work of research with largely in collaboration with Dalhousie University. So that work was started in the laboratory, working on ocean alkalinity enhancement at its most basic way, and sort of in beakers, and it was all leading towards doing this in the field, and that's what happened last fall. So for the months leading up to it, Planetary was focused on finding and qualifying an alkalinity source that could be dosed into the ocean safely and effectively, and that's what we did, as well as working with the DAL team to organize a field trial that would provide the most robust data. The DAL team was a big part of that. They were doing independent research to study the safety and efficacy of our work. So we collaborated closely together, but the work itself is done independently. So that started for about a 2-month trial that lasted last fall. It was incredibly intense, and we learned an incredible amount, and it's was sort of continue our work in other places, but also in Halifax.
Awesome. That's super helpful. So we'll keep with you for now. Could you talk a little bit about the actual results? I know you worked specifically on the ecological impacts, so could you run us through those a little bit?
Yeah, so what you're seeing behind me is actually sort of the dosing system sitting in Halifax Harbor. And so the alkaline material went kind of right out, as you can see in that image. And we were monitoring for biological and chemical changes. So from a biological perspective, we had a couple of really important results. First and foremost, we identified as a key risk, both from the academic literature and from what we knew about our area, that accumulation of the material on the seabed, and particularly impurities in the material, like heavy metals, are a big risk that we had to keep a close eye on. So we built a drop camera system that we could deploy from boats to take visual images of the seabed. We collaborated with Dr. Chris Algar's group at Dalhousie to collect sediment cores and image them so we could see if any of this stuff was accumulating. And those images didn't show any visible accumulation of this material. It's essentially a white powder, and it would have shown up on the dark colored sediment, or so we thought. So that was the first step. And the second step was then taking the sediment samples we collected and taking the surface of those samples and running them for elemental analysis. So are we seeing changes in the actual metal content of that sediment? And what we found there was a few things. One, the sediments themselves are already very full of metals. Halifax Harbor is fairly contaminated, over 200 years of an industrial activity. That's not new information, but now we've got a good baseline of those levels. We find that over months, we've been doing this for almost a year, that the levels change a fair bit from month to month. There's a fair bit of variability. But during the dosing period, there was no clear indication of a spike in those metals. And any increases that we did see, particularly in magnesium, because the compound we added was mostly magnesium hydroxide, quickly went back down if there was an increase, indicating sort of dissolution or sediment suspension, resuspension. So that was the sediment story, and those samples are being continued on now, and they will be for the foreseeable future. We also collected samples on the phytoplankton community, which is sort of the microscopic algae at the base of the food chain. There's been a fair bit of research about that being a really important group to study for impacts. So we collected water samples upstream of where we dosed the alkalinity, as well as downstream of where we dosed the alkalinity. And we wanted to compare how the phytoplankton community might change from these two water samples. So we collected those samples and shipped them over to Dalhousie each day for about a month. And a master's student at Dalhousie named Marie Eggert out of Dr. Hugh McIntyre's lab was studying the photosynthetic efficiency, or in other words, just how capable the plankton would be at photosynthesizing, which is their key process. And she didn't see any statistical difference in the upstream versus the downstream samples. She's going to publish this work in the coming months, so we're excited to see that come out. But that was an encouraging result.
Yeah, it sounds like it.
Last thing to mention from the biological side is that there's other work that's been done. So a group, Dalhousie's looking at environmental DNA as a way to sort of track the community as a whole over time. That work is all underway, and hopefully will be published in the coming months as well. So that's the biological story. The chemical one, we saw a lot of interesting things. So we saw the acidity levels, so the pH is how we measure that. It's called pH. We saw that the natural variability at this location is really high, and that's mostly driven by tides. That created a pretty big challenge because we wanted to be able to detect our change in acidity, the decrease in acidity, directly. And the high natural variability made that very challenging. But the other side of that is that if you are seeing a high amount of natural variability, that probably tells you that the small changes we're trying to make on top of that won't have an impact on the ecological systems in terms of how they care about chemical changes. So it was a challenge, but also created a bit of assurance. Importantly, we also saw the alkalinity go up. So ocean alkalinity enhancement, we did detect an enhancement of the alkalinity.
Awesome.
It's good news. And that was work done mostly by Daria Atamanchuk at Dalhousie and her team, as well as Dr. Ruth Musgrave. They baselined the system very well. So they had a really strong understanding of how the alkalinity varies in the harbor. And so we can see a change in that during the time of the trial and the recovery of the system back to baseline after the trial. And that's a really powerful result. And Daria will be publishing that in the coming months as well. So that was really exciting. Finally, from a modeling perspective, and Steve will touch a bit on this later, we saw mostly from Dr. Katja Fennell's group, a lot of the CO2 uptake was happening locally in the harbor, and her model was able to nicely show that. And the model also showed that the changes in the CO2 levels between the air and the ocean, which is another thing that we're trying to do actively, those gradients can be pretty high. And that gives us hope that in the future, we'll be able to measure those gradients directly. So this year, we're going to go out and try and do that. But learning that from last year was very valuable. So, overall, it was very challenging logistically, and we'll talk a bit about that later. But the results we got, we learned an incredible amount.
Yeah, it sounds like it. Thanks for sharing all of that. For those of you listening that are less auditory learners and more visual learners, we do have our impact report coming out soon, so you'll be able to dig into detail on what Will just told everybody. Okay, thank you. Steve, you get to answer a fun question. Not that ecology and chemistry is not fun, but did we remove carbon? What were the results from last year?
Yeah, thanks, Jen. That's a very important question, of course. That's the fundamental objective of the whole exercise. And I think we can be confident that we did remove net carbon as a result of the pilot. It's not as straightforward as terrestrial techniques like direct air capture, for example, where you can actually physically measure the amount of CO2 that you capture as you pump it into geological storage. So dealing with the ocean is a lot more complicated, but perhaps I can walk you through the kind of process that we use to come up with an estimate of the CO2 removal. So we start out with the mass of the feedstock. So we're using a mineral which is primarily magnesium hydroxide, brucite derived, which is mined in China and then ground down to a fine powder. So we start with the mass of that, which for this trial was about 278 tons of basically dry feedstock. We need to know how much of that material is actually going to contribute reactive alkalinity. So as Will mentioned, magnesium hydroxide is the main component of that, but there are other minerals in there as well, things which will not dissolve. A significant one is calcium carbonate, which obviously is also prevalent in the ocean, but won't dissolve in the surface, fortunately for lobsters and shellfish and other calcifying creatures. So we do mineralogical analysis of the material to find out what the range of metals is, range of oxides, how much carbonate, sulfur is contained in it, and we can then determine the effective reactive alkalinity content. And for the material that we were using last year, that turned out to be about 66%. So if you multiply those two numbers together, you get the kind of mass of effective alkalinity expressed as a magnesium hydroxide equivalent that we dosed into the ocean, and that turns out to be just over 180 tons. So when the magnesium hydroxide hits the ocean, what happens is that the hydroxide basically converts dissolved CO2 in the water into bicarbonate and carbonate ions. So the concentration of dissolved CO2 goes down, and that effectively creates space for more CO2 to diffuse down from the atmosphere without adding to acidification. So that's kind of basic ocean chemistry, which has been studied for decades. You can calculate what the ratio is then of the mass of CO2 that will be drawn down into the ocean for each mass, for each ton per ton, for example, for each ton of reactive alkalinity that you dose into the ocean. That ratio depends upon the ocean conditions. And in Halifax and the Scotian Shelf, you've got pretty cold waters, around 3 degrees at the time in the fall when we were carrying out the pilot. You've got a relatively low pH, relatively high acidity, and a relatively high amount of CO2 dissolved in the water. So the efficiency number is quite high. It's about 1.38 tons of carbon dioxide removal for each ton of reactive alkalinity that you dose into the ocean. So if you multiply that by the 182 roughly tons of alkalinity that we dosed, you get the theoretical maximum amount of carbon dioxide removal that you could achieve if everything worked in a perfect world. And that number turns out to be just over 250 tons. So theoretically, you could achieve 250 tons roughly of carbon dioxide removal. Now, for that, the CO2 removal to take place, the alkalinity and the CO2 depleted water has got to stay in contact with the surface of the ocean, because it's only at the surface that CO2 is going to be drawn in. And ocean mixing, the subduction of water, and various other processes can cause that PCO2 depleted water to lose contact with the surface. It can be advected, transported off the shelf into the deep Atlantic, for example. So the way we go about quantifying that, as Will alluded to, is using ocean models. And we use a kind of multi-level approach to this. So in what we call the near field, which is the Bedford Basin, Halifax Harbour, and the nearer part of the shelf, extending perhaps 30 kilometers or so offshore, we're using a model which has been built by Catcher-Fennell's group at Dalhousie over the last many years. So they built a fairly detailed set of models, look at all of the processes taking place in the harbour and the basin, and that's used then to model the kind of movement and transport of the alkaline material in the harbour, in the basin, out onto the shelf, and the first stages of carbon dioxide removal. We then couple that, what we call a near field model, to what we call a far field model, which is actually a global circulation model that models the ocean circulation of the whole planet. Now that might seem like a bit of overkill, but it's a well-recognized tool which has been used for a number of peer-reviewed studies of ocean alkalinity efficiency. So it's a good tool for us to use in this study. So we basically couple the near-field model with the far-field model. We transfer the alkalinity that moves out of the near-field domain into the far-field model, and then we calculate the additional carbon dioxide removal that is taking place as the PCO2 depleted water is transported down the shelf, basically kind of southwest, down towards the Gulf of Maine and further, eventually merging in with the Gulf Stream. So those two sets of models together give us an estimate of the actual amount of gross carbon dioxide removal that's taking place in the ocean. And the number we get is a little shy of 230 tons. So if you compare that with the 250, just over 250, which was the theoretical maximum, we're seeing an efficiency of around 90%, which fits very well with the kind of global studies which have been published, looking at how efficient this process could be if implemented in different parts of the world.
Mm-hmm.
So that gives us what we call the gross removal number for the project. And obviously, the project itself resulted in a significant amount of CO2 emissions, starting from the mining, the grinding of the material, transportation across the Pacific to initially the US Gulf Coast and then up to Halifax, the construction of dosing and sensing equipment for the project, the accommodation and transportation of staff, the flights to Halifax, for example. So we do what we call a life cycle analysis, starting at the very beginning of that process and working through to the disposal of all of the equipment and materials and waste at the end of it. And that tells us that the project itself was the cause of roughly 80 tons of CO2 emissions. So if we deduct that number from the previous number, which was just shy of 230, we get roughly 145 tons of net carbon dioxide removed through the project. Now that's a kind of a mid-case estimate. So probably roughly 50% chance of the actual number being higher or lower. What we want to do is to arrive at a high confidence level. So we examine the uncertainties on all of the factors that have contributed to that. So going back to the mass of the feedstock, how accurate was the weighing of that material? Did we lose any of it during the operations? The mineralogical analysis, what was the kind of range of uncertainty around that? How heterogeneous did we find the material to be? And then we look at the ocean models. How is it affected by the wind speed? How is it affected by various other assumptions that go into the model? We look at the uncertainties around each of the components in the life cycle analysis, the range of uncertainty on carbon intensity of a container ship, for example. And so we combine all of these uncertainties and we work out a range of uncertainty for the final net CDR number. If you think about it as a normal distribution, one standard deviation, basically, if we deduct one standard deviation from the mean value, we end up with a value which has got a relatively high confidence, a probability basically of about 84% that the actual number will be higher than that. So that's what we call our high confidence number. In this instance, the uncertainty analysis comes to about 10 to 11 tons as the standard deviation. So we subtract that and end up with a number of around 135 tons as our high confidence estimate of the net CO2 removal. So it's a long answer to a fun question, but yeah, we're confident that we had a positive result and that we can quantify it with that kind of degree of certainty.
Got it. So those numbers will be verified later on, but roughly in that range.
Indeed, thank you very much. They are still provisional numbers. The modeling work is still being finalized. Once we've done it and we're happy with the robustness of the work we've done, there'll also be a third-party independent verification that takes place.
Okay, excellent. Well, thank you for the answer there. Given what you both know now, what are you planning to iterate upon in 2024 throughout the whole process? There must be lessons learned that you're taking forward.
I'll go first. There's so many things to improve upon. So, the trial itself was hectic in nature. It was the first of its kind, both for us and for the collaborating parties. So, we have a lot of work to do to streamline things, make it easier for us to get the alkalinity in the water in a safe way, make it easier for our partners to go out and measure it effectively, and also to communicate what we're doing. We did the best job we could last year, but we know that we can do better. So this year we've got folks like you, Jen, to help us make sure that that everybody's up to speed on what we're doing. If people have questions, that they'll get answered promptly, and all that sort of stuff. The way in which we observe it, the sensors that we use, we had a bunch of sensors not work the way we wanted them to last year, which is very typical for ocean field work. So this year we've made big improvements on the types of sensors we're using, the way in which we can take that data quickly and process it and adjust accordingly, making sure that, if the data is looking, concerning, for example, that we can stop dosing immediately. Thankfully, we didn't have to do that last year, but as we scale to higher volumes, that may happen. And so we have to be, really ready to shut down if something isn't working well. So lots of improvements to be made from last year.
Yeah, sounds like a lot of great lessons learned, though.
Yeah, absolutely.
Steve, did you have anything to add to that?
Indeed, for me, I think the measuring on the measurement front and on the the modeling front, I think there's a lot that we can improve on. I think we should recognize that we're really taking here the first steps in a journey that's going to last for decades. We're able now to measure a very small signal in the ocean. Hopefully, as we scale up, we'll be able to progressively move out to larger scales and measure the chemical impact of what we're doing. And I think the first steps in that, as Will alluded to, trying to measure the difference in CO2 partial pressure between the atmosphere and the ocean, is a very exciting step. And similarly, on the modeling front, we're using a toolkit which was not designed for this with this kind of application in mind. We're doing the best we can with it, and we've had feedback from experts that they think we haven't done a bad job, which is encouraging. But again, there's a huge amount of development work to be done here, and one of the things which is very common in climate modeling is what you call a model intercomparison study, where you get many different research groups who have built different models with different assumptions, different numerical systems to work on the same problem and compare their results. And it's only by going down that kind of route that you can really have confidence in the modeling. And what I've described, our kind of modeling approach at the moment, is a first step along that route. I'm really looking forward to getting to a condition where we've got multiple groups working on the same problem, and we can really compare the models and give ourselves confidence that what we're doing is robust, and also tell us how much detail we need to incorporate into those models. So, this is going to be the next step. We're going to make improvements on both of those fronts, and I'm really looking forward to what comes out of it.
Yeah, let me jump in quickly to say that is a big goal for this year and a big part of our objective. We're actually, there's something that's come out in Halifax called the Joint Learning Opportunity that's bringing external parties in, and actually providing funds to bring external parties in so that they can do this sort of thing from a measurement perspective, from a social science perspective. And this is the really critical thing about these types of field trials, especially this one being sort of the first of its kind, is that it's going to facilitate this type of collaborative work. It's no longer theoretical, right? We're doing this for real. And that allows real data to be collected and study it instead of, theoretical studies, which are really what we've got so far. Yeah. So yeah, it's a big step, and we're going to learn a lot from last year and the years to come.
Thank you both so much for your time. If you don't already, please go ahead and follow Planetary on LinkedIn, Instagram, and Twitter. You can get updates on our projects there. And important to note, we're publishing our 2023 impact report very soon. This impact report summarizes our Halifax trials in great detail. So everything Will and Steve just mentioned, you can go dig into that pretty deeply in that impact report. Thanks for joining us and for being part of the Planetary community.